Okay, let's unpack this. Imagine you're relying on an AI, maybe a navigation app, and it just confidently says, turn left here. Here.
Ah!
But then, bam, you find out it's leading you straight into I don't know, a massive construction zone, a blocked road.
Right. Or think about medical AI. If it gives a diagnosis with absolute certainty, zero doubt expressed,
Yeah,
and it turns out to be critically wrong, it's not just annoying, it's potentially dangerous.
exactly. These aren't just like minor glitches. There's situations where a super confident prediction, without any sense of how sure the AI actually is, well, it can lead to pretty serious problems.
And that's really why today we're taking a deep dive into probabilistic AI.
Mm-hmm.
This isn't just some small technical update. It feels like a really profound shift in how AI actually grapples with uncertainty. The real world's full of it, right?
Absolutely. It's messy. So our mission today really is to explore what probabilistic AI actually is. We want to get into its core methods, things like Bayesian approaches, Gaussian processes, and also highlight its transformative impact across different industries, and then look ahead a bit. What are the challenges? What's exciting on the horizon? So if you're into tech, maybe a professional trying to cut through the hype and really understand a key AI concept, well, I think you'll find this useful.
Yeah, and what's really fascinating, I think, is that this isn't just about better algorithms. It's almost a philosophical shift. Some people are calling it humble AI.
Humble AI. I like that.
Think about it, right? Traditional AI might just spit out, rain tomorrow. That's it. One single deterministic answer.
Mm-hmm.
But probabilistic AI, it approaches that totally differently. It gives you a range like, okay, there's maybe a 70% chance of rain.
Mm-hmm.
And crucially, it might even add a confidence interval. It could say, look, the true chance is probably somewhere between 50% and 90%. That ability, that quantification of its own confidence is just vital for trust, for safety, for actually making better decisions.
Okay, so let's lay down the basics then. What is probabilistic AI, fundamentally? It's about moving past those single lonely predictions, isn't it?
Exactly. Instead of just one guess, these systems are designed to explicitly model uncertainty and quantify it. They can tell you effectively how reliable their own predictions are.
That weather example nails it, right? Knowing there's a 70% chance of rain, but with that 50 to 90% range, that completely changes how you might plan your day compared to just rain.
Totally.
It shifts the focus. It's not just what the AI thinks, but how sure it is about it.
And that brings us to a really key distinction, the two main types of uncertainty that these models have to deal with.
Okay.
First off, there's what we call aleatoric uncertainty. Think of this as the inherent randomness, the noise that's literally in the data itself.
Right, like errors from a sensor maybe,
Mm-hmm.
or just natural fluctuations.
Spot on. Sensor noise, measurement inaccuracies, the kind of built-in variability in really complex systems. And the key thing here, this type is irreducible.
Irreducible, meaning
Meaning you just cannot get rid of it completely. It doesn't matter how much more data you throw at it or how perfect your model becomes. It's just part of the observation process.
so you're saying some uncertainty is just baked into the universe almost. We just have to live with it.
Pretty much, yeah. It's the background noise we can't completely silence. But then there's the second type, epistemic uncertainty.
Okay, what's that?
This one is all about the model's own ignorance. It's lack of knowledge, you could say.
So this is the model saying, I don't know enough about this situation.
Exactly. It happens when the model hasn't seen enough training data for a specific scenario, or maybe its internal structure, its architecture isn't quite complex enough to capture everything.
But the good news here.
The good news is that epistemic uncertainty is reducible. You can often tackle this one.
Oh, more data.
More data helps, yeah. Or improving the model design, maybe using more sophisticated learning algorithms. There are ways to reduce the model's ignorance.
That makes a lot of sense. So knowing which type of uncertainty you're dealing with is really crucial. It tells you how to try and improve things, or if you just need to accept the limits.
Precisely.
If it's mostly aleatoric, throwing more data might not do much. You just acknowledge the noise.
Mm-hmm.
But if it's epistemic, well, there's a path forward.
Right.
And you mentioned some models, like Gaussian processes,
Yeah.
are designed to handle both.
That's right. They're built with that kind of dual awareness in mind.
So, okay, how do we actually build these systems, these uncertainty-aware AIs? Where do we start, practically speaking?
Well, it gets us into the core methods. And yeah, often the conversation starts with Bayesian methods.
Right.
If you think about the big picture, Bayesian methods are really the mathematical foundation that lets AI learn incrementally, step by step, and constantly update how confident it is based on new information.
It's about updating beliefs, isn't it?
Exactly. The core idea is updating beliefs, using evidence.
Yeah.
You begin with a prior belief, that's your initial guess or your existing knowledge.
Okay.
Then, as new evidence comes in, you use something called Bayes' theorem to mathematically combine the prior and the evidence. And that gives you a posterior distribution.
Posterior, meaning after seeing the evidence.
Yep. It's like a continuous refinement process. What you thought you knew meets what you just learned.
The doctor example works well here, doesn't it?
Yeah.
A doctor starts with a prior belief about how likely a disease is, just based on general knowledge.
Mm-hmm.
Then a test result comes back. That's the evidence. They update their belief. And they don't just get a yes or no. They get something like, okay, now there's an 80% chance of this disease given these specific symptoms and test results.
Exactly. It quantifies the certainty, which is incredibly useful for making clinical decisions.
Yeah, you can see how that's powerful.
And a really key benefit of Bayesian models is that they naturally give you a full probability distribution over the possible outcomes, not just a single number. This distribution directly shows their confidence, or lack thereof.
But weren't they traditionally quite computationally heavy?
They could be, yes. Historically, for very large data sets, the calculations were intensive. But modern techniques have made a huge difference. Things like Markov chain, Monte Carlo MCMC, or variational inference.
Those sound complicated.
They are sophisticated statistical sampling methods, basically, but they've become much more efficient, making Bayesian approaches far more practical now, even for pretty big problems. That's why we've seen such growth in their use recently.
Okay, got it.
Right.
So let's shift gears slightly. You mentioned Gaussian processes earlier. I love this idea. Imagine a model drawing its prediction not just as a line, but with like a shaded band around it, showing visually how unsure it is.
Right. That's exactly what Gaussian processes, or GPs, do so well. They're really powerful probabilistic models, especially for what we call regression tasks.
Regression. So predicting continuous values, like temperature or maybe stock prices.
Exactly. Temperature, prices, pollutant levels, things like that. The core idea behind GPs is a bit mind-bending. It's like thinking about a distribution over functions.
A distribution over functions.
Yeah. So imagine you have a few data points on a graph. There are infinitely many smooth curves or functions that could potentially fit through those points, right? A GP essentially assigns a probability to every single one of those possible smooth curves.
Wow. Okay.
And so when you ask a GP to make a prediction for a new point, it doesn't just give you the single most likely value. It also calculates the variance or spread of all the probable function values at that point.
Ah, and that variance is the confidence estimate.
Precisely. So you get that 20 degrees Celsius plus or minus 2 degrees kind of output. It gives you the range, the uncertainty built right in.
And they're flexible too, I hear.
Very. They're non-parametric, which basically means they can adapt to fit really complex patterns in the data without you having to pre-specify a rigid functional form. And they do this while naturally spitting out those confidence levels. That's why they're so valuable in areas like robotics for safe path planning or geospatial modeling, time series forecasting, anywhere that knowing the model's confidence is key.
Okay, so we have these foundational methods, Bayesian and GPs. But how do they connect with the huge advancements we've seen in deep learning? Because standard deep learning models can sometimes be overly confident, right? Like a black box just giving an answer.
That's a critical question. How do we get these incredibly powerful, complex deep learning models to be a bit more humble, to tell us when they're unsure?
Yeah.
That's where the integration comes in. We talk about probabilistic deep learning, or sometimes Bayesian deep learning, BDL. The whole goal is to merge the power of deep learning with the principled uncertainty handling of probabilistic methods.
And how does that work? What are the techniques?
Well, there are a few key approaches. One is Bayesian Neural Networks, or BNNs. Instead of having fixed numbers for the connections, the weights in the network, BNNs place probability distributions over those weights. This inherently allows the network to express uncertainty in its outputs.
Okay, that sounds cool. What else?
Then you've got things like Variational Autoencoders, VAEs. They're a type of generative model good at learning compressed representations of data, but they do it in a way that explicitly includes uncertainty in those representations.
Right.
And another interesting one is Evidential Deep Learning, or EDL. This tries to get the network to directly output not just a prediction, but also the evidence it has for that prediction, which can then be used to quantify specifically the epistemic uncertainty, the model's own ignorance, often without needing the computationally heavy sampling that BNNs might require.
So the synergy here, the combination, it lets these powerful deep learning models be accurate and tell us how confident they are.
Exactly. And that's absolutely essential if we want to deploy these models safely in high-stakes areas like medicine or autonomous driving. It's fundamental for building trust.
And you mentioned computational costs earlier.
Yeah.
Has progress been made there for these deep probabilistic models too?
Yes, definitely. While the complexity was a major hurdle, modern algorithms like variational inference have become much more sophisticated and efficient, combined with advances in Monte Carlo methods and just raw compute power from things like GPUs.
Right, for hardware helps.
It's made probabilistic deep learning much more practical and scalable than it used to be. We can now apply these principled uncertainty methods even to really large, complex models. That gap is closing.
Okay, this is fascinating. Let's move to the impact then. How is all this actually playing out? Where are we seeing probabilistic AI making a real difference? Because you said it's about better decisions, not just better predictions.
Right, and the examples are really starting to pile up across different fields. It's quite eye-opening.
Let's start with healthcare. That seems like an obvious place where uncertainty matters hugely.
Absolutely. Probabilistic models are really changing things. They help in diagnosis by giving probabilities like that 70% chance of pneumonia idea, but also confidence intervals around patient outcomes.
And are there actual results? Numbers?
Oh, yeah. Some studies have shown really impressive impacts. Things like a reported 42% decrease in hospital readmissions related to medication issues when using probabilistic tools for risk assessment.
Wow, 42%.
And 65% earlier detection of adverse drug reactions by monitoring patient data probabilistically. Even in radiology, AI systems are now being designed to flag, say, 15% of cases where the model itself is uncertain, prompting review by a human specialist. That prevents the AI from making potentially dangerous, overconfident mistakes.
That's incredible. Okay, what about self-driving cars? Talk about high stakes.
Definitely high stakes. Autonomous systems like self-driving cars rely heavily on probabilistic models, especially for perception.
Perception, like
Right.
identifying objects.
Exactly, gauging the confidence of what they see. Is that object a pedestrian, a bicycle, a plastic bag? The AI might assign probabilities like 90% chance this is a human,
Okay.
but crucially, if conditions get tricky, maybe it's foggy or the sensor data is noisy, that confidence might drop. Let's say it drops to 60%.
Right.
A probabilistic system can then be programmed to react cautiously. Maybe it slows the car down, increases following distance, or even requests human intervention. It effectively says, I'm not totally sure here, so I'm going to play it safe.
And does that actually make a difference in safety?
The data suggests it does. Test scenarios using these approaches have shown things like a 23% reduction in simulated accident rates compared to more deterministic systems. It's about adaptive, risk-aware behavior.
That makes sense. Playing it safe when uncertain.
Yeah.
Okay, moving away from immediate safety, what about finance? How does probability play in there?
Finance is another huge area. Think about risk management. Bayesian methods, Monte Carlo simulations, these are workhorses in finance.
Well, what kinds of things?
Credit risk assessment, fraud detection, pricing complex derivatives like options. Instead of just a single prediction of default risk, they provide a whole distribution of potential financial exposures.
Giving a range of possibilities again.
Exactly. And the impact is measurable. For instance, Bayesian credit risk models have demonstrated reductions in default prediction errors by around 34%. And some credit scoring models achieve high accuracy, like 97%, but also identify the specific high-risk predictions where the model is uncertain and human review is needed. It's about managing risk intelligently by understanding the full spectrum of possibilities, not just the most likely one.
That's really interesting. Okay, two more areas. What about scientific discovery or environmental modeling?
Yeah, big applications there too. Gaussian processes, which we talked about, are great for modeling environmental phenomena, predicting rainfall patterns, air quality levels, but always with those crucial uncertainty estimates. That's vital for planning, for resource allocation.
Meaning the range of possibilities helps decide what to do.
Exactly. And in broader scientific research, AI automation guided by probabilistic principles is speeding things up. Think drug discovery or materials science. There's evidence that GP-guided molecular design, where the AI suggests experiments likely to yield the most information given current uncertainty, can cut experimental costs by as much as 65%.
Wow. By being smart about uncertainty.
Yes, focusing effort where it's most needed to reduce the model's ignorance.
And finally, you mentioned large language models, LLMs. How does uncertainty fit in there?
That's a really active and important area right now. LLMs are starting to incorporate uncertainty estimation more explicitly.
Why? To stop them making things up.
Essentially, yes. It helps in detecting hallucinations. Those times the model generates text that sounds plausible but is factually incorrect or nonsensical. If the model can indicate when it's less confident about a statement it's generating, that gives us, the users, a much better signal about when to trust the output and when to be skeptical. It's a key step towards making these powerful models more reliable and enabling better human-AI collaboration.
It's really amazing to see these numbers, these concrete examples. AI that admits, I don't know, isn't just a cool idea. It's actively making things safer, more efficient, more reliable across the board. But it can't all be smooth sailing. What are the main hurdles? What challenges still exist in this field?
You've hit on a key point. Yeah, despite all the progress, there are definitely still challenges. Computational complexity and scalability remain concerns.
Still, even with the advances.
Yes, especially for exact Bayesian inference on truly massive data sets, or for extremely complex deep learning architectures. It can still be very computationally intensive. Approximations like variational inference help a lot, but there's often a trade-off.
Okay, well.
Another big one is uncertainty calibration. Making sure that when a model says it's 80% confident, it's actually correct about 80% of the time in those situations. Getting that calibration right, especially with deep learning models, which can sometimes be systematically overconfident or underconfident, is tricky but crucial for trust.
Right, you need the confidence level to actually mean something reliable.
Exactly. And then there's interpretability.
The black box problem again.
Sort of. Even if a model tells you how uncertain it is, understanding why it's uncertain about a particular prediction can be really difficult, especially with deep learning. Is it because the input data is weird, or is it because the model just hasn't seen anything like it before? Unpacking the reasons for uncertainty is still an active research area.
Okay, so those are the challenges. Looking ahead then, what's exciting? Where's the research heading? What are people pushing towards?
Well, there are several really exciting frontiers. One big area is creating deeper synergies with causal AI.
Causal AI, understanding cause and effect.
Exactly. Combining probabilistic reasoning about uncertainty with the ability to infer actual cause and effect relationships. The goal is AI that not only predicts reliably, but understands the underlying mechanisms, making it more generalizable and interpretable. Imagine an AI that knows why it's uncertain.
That sounds powerful.
Very. Another huge focus is just generally advancing trustworthy and explainable AI, often called XAI. Uncertainty quantification is absolutely fundamental to this. Making AI systems that are robust, reliable, safe, and transparent. Well, understanding and communicating uncertainty is key to all of those.
Makes sense. What about the computing side?
There's ongoing work there, too. People are exploring things like quantum-enhanced probabilistic computing, though that's likely further out. And specialized hardware, like neuromorphic chips, could potentially offer new ways to perform these kinds of computations efficiently.
Interesting. And you mentioned LLMs earlier.
Yes, foundation model uncertainty is a massive topic. Figuring out the best ways to rigorously quantify and manage uncertainty in these huge pre-trained models like GPT-4 or Claude, that's critical for their responsible deployment. It's really about making AI not just smarter in terms of capability, but smarter in terms of self-awareness and responsibility.
What a journey, really, through this whole world of probabilistic AI. If you had to boil it down, what's the single most important takeaway from all this?
I think ultimately embracing uncertainty is a really profound philosophical shift for AI itself.
A philosophical shift. How so?
It's moving AI away from just chasing the highest possible prediction accuracy, often blindly, towards becoming what we called humble AI, an AI that recognizes its own limits.
Right. Less blind guesses.
And more calibrated confidence. And that shift is incredibly empowering for us humans, for the decision makers. When the AI gives you not just an answer, but the whole spectrum of possibilities and how likely they are, you can weigh the risks and rewards much more effectively. It transforms AI from just a predictor into a really sophisticated partner in decision making.
So, thinking about our listeners, what does this all mean for you as AI keeps evolving and becoming part of our everyday lives? Maybe. Maybe the most powerful AI, the most intelligent AI, won't actually be the one that pretends to always be right. Maybe it's the one that's honest, the one that tells you when it might be wrong. That feels closer to real intelligence, doesn't it?
Yeah.
It's closer to how we humans think, constantly weighing probabilities, dealing with ambiguity. That's a great way to put it.
And maybe that honesty is what prepares us for deeper, more trustworthy partnerships with AI in the future. That feels like where the real intelligence lies.
And that pretty much wraps up our deep dive today into the fascinating world of probabilistic AI. We've seen how getting AI to embrace uncertainty isn't just a technical tweak. It's a fundamental change, driving more robust, more reliable, and ultimately much more valuable AI systems. Systems that understand and can actually communicate what they don't know. So we really encourage you listening to maybe reflect a bit. How could quantifying uncertainty impact your own work, your field, or even just your daily interactions with AI systems? How might knowing how sure an AI is change how you make decisions based on its output? It's a really critical area, and honestly, there's always more to explore. Thank you so much for joining us on this deep dive.